In this video, we're going to be talking about evaluating integrals by using what's called the limit of the Riemann sum. And if you remember in my last video, I did a bunch of rectangles. I did a bunch of rectangles to approximate integrals. We would, if we had like some graph or something like that. And basically what we did was we just divided this into a certain amount of rectangles or something like that. And we approximated it that way. And we would just make our attempt like that. But remember what that was all about. You remember that the width of it was just delta x. So the width of each of these rectangles was delta x. And then the height was, well, the height was simply just, it was f of x I star, where that basically means it's some point uh, on this rectangle. It's at some point down here. We don't really know what it is, but it's wherever this, it could be a left endpoint where the top left corner intersects the curve, or the right endpoint where the top right corner intersects the curve, or it could be the midpoint. And this f of xi star basically means that, hey, this can be any one of those. It can be left, right, midpoint, or anywhere in between. So remember what we did. We basically just did, we did delta x times f of x1. So sorry about that. F of x1. So that was our first rectangle, right? And then plus delta x times f of x2 plus delta x times f of x3, and so on and so forth, right? And then remember, I condensed that a little more. I said, hey, let's just factor out the delta x. And, this will be f of x1 plus f of x2 plus f of x3. But here, there's an even better way to write this. And an even better way to write this is by using the Riemann sum. So the Riemann sum is essentially the same thing. So the Riemann sum, it's saying the same exact thing, but instead of just adding this on forever and ever, we're gonna condense it into a sigma. So we're just gonna use a sigma like this, where our upper limit is n, index is I, lower limit is 1. Okay, and then you basically just, it's f of xi star. Now, don't be intimidated by the xi star. That just means this is basically just the height of each little rectangle, and then times delta x. So this is an approximation. So this is an approximation of our area. So approx of area. And recall that just this f of xi star part, that's the height. And this delta x is the width of each little rectangle, But, after a little while, people started figuring out that, hey, what if we just broke this up into infinitely many rectangles, or like what if we broke this up into infinitely many rectangles, then we would get the exact area under the curve. And in order to do that, well, our area, it wouldn't be an approximation like this anymore. It would actually be exact. So our area then becomes the limit of the Riemann sum. So it's the limit as n approaches infinity, where that n just stands for, hey, that's the number of rectangles that we're going to use to approximate the area under this curve. But since we're using infinitely many rectangles, then hey, this actually becomes the area under this curve. It's the precise area. And so there you have it. It's just the area equals the limit as n approaches infinity of, the sum of f of xi times delta x. And again, f of xi star, that's still the height, and delta x is still the width. And that's all it means. And another notation you might want to familiarize yourself with is oftentimes books will write this in an integral. So what I want to point out is this. I want to point out that what I just wrote, the limit as n approaches infinity, so that was bad infinity, of the sum, so just sigma, f of xi star, delta x, that's the same thing as this symbol right here. It's the same thing as the integral from a to b of f of x dx, where this dx simply means with respect to x. And there's just differential x. So these both mean the same thing. All a to b is, those are your limits of integration. Essentially, what it was before. Remember, we would say, hey, this is from -1 to 3, right? Like we would be asked to approximate the area over that portion. Well, that would be our limits of integration. This would be a -1, and this would be a 3. So it'll be obvious what those are. And then f of x is really just f of x is really just the function you're really dealing with. You just don't have an xi star anymore. And dx, delta x becomes dx in this case. And that's really all you have to know. So let's just do a quick example where we kind of just swap back and forth between these two notations. So let's say I had, I'm gonna just write example over here. So example, and let's say I was given the limit as n approaches infinity of, let's say, sum, so sigma, and I equals 1. And this is the function we're dealing with. We're dealing with 5 xi star cubed plus square root of xi star minus 4 sine xi star, and then times delta x. And I want this in integral form. Well, okay, let's do this. And also I should mention that we're given the interval from 0 to pi. So this is a, and this is b. So what I have to do here is I have to decide, what are my limits of integration? Well, those are given to me right off the bat, and they'll always be given to you. So 0, the first one is always your lower one, so 0 down here. And then the next one, or the last one, is always your upper one, so from 0 to pi. Okay, and then now I'm just going to write all of this. So instead of these xi's, I'm just going to write x's. So it's going to be 5x cubed plus the square root of x. So again, instead of these xi stars, I'm writing just x minus 4 sine x. And remember, the delta x becomes dx. So dx right here. And that's really all there is to this. So again, there's not really many steps in converting from one form to the other. It's really just a matter of recognizing it. And, just by seeing this, we're going to be able to go the other way around. We'll be able to go from integral to limit of the Riemann sum. So that's just something else to keep in mind. So I'm going to clear the board. And again, if you want to just slow down or take a screenshot of this or rewind the video, that's perfectly fine. I'd especially just remember the limit of the Riemann sum. That's definitely a very important problem. And let's just do one more example, though, of dealing with the limit of the Riemann sum. So let me clear this. Okay, so let's say we were given f of x equals x squared plus the square root of 1 plus 2x. And we're working from 4 to 7. And all we want is we just want this in Riemann sum form, and that's mostly what these problems will ask, especially if it's one as complicated as this. So what we have to do here is we really just have to be able to put this in, we just have to put this in a Riemann sum. We have to compute our delta x, and we have to be able to just find out what this function is, and we have to, in terms of xi. So the first thing you always want to do here is you want to compute what delta x is. So delta x, remember that's b minus a over n. So in this case, it's 7. It's over here. This is b. So this is b right here, and this is a. So 7 minus 4 over n. We're going to get 3 over n. And we don't know what n is, So you just want to leave it like that, because if we're asked to put this right here in in a Riemann sum, we don't know what n is, so you're just going to leave it as that. And then another thing you want to do is you want to have xi, and this is just another formula to know. It's a plus delta x times I. So where a is simply your starting limit of integration, and delta x is simply your delta x, and then that's multiplied by an I. So my a here is 4, my delta x is 3 over n, and that gets multiplied by an I. So to write this a little more nicely, I'm going to write 4 plus 3i over n. So now we just use our limit of the Riemann sum definition. So it's limit as n approaches infinity, sigma, and everything stays the same over here. So n, I equals 1. And what we want to do is we want to, wherever we see an x, we want to plug in an xi. So I would have 4 plus 3i over n squared plus the square root of 1 plus 2 times 4 plus 3i over n. And then this all gets multiplied by delta x at the end, remember. So this is just going to be multiplied by 3 over n. And that's really all there is to it. So most of the times, if the book asks you to just write an expression, in the Riemann sum notation, then you would simply start by computing your delta x, and then you'd find delta xy, or sorry, not delta x, you'd find delta x, and then you'd find xi, and then you'd basically just put them both together. Wherever you see an x in your original function, you would put the xi, and then you multiply all of that by your delta x. And if it just simply asks you to, hey, like just write it in this notation, do not evaluate the limit, you would just leave your answer like this. But, another part of this though is, hey, what if we do want to evaluate this and we do want to calculate the area? And that's what I'm going to be covering in my next video. I was hoping to get around to it here, but I'm going to run out of time and I don't want to make this video like 30 minutes long or something. So stay tuned for the next video, and in there I'm going to talk about evaluating these limits of Riemann sums, and from there we'll be able to get the actual area under a curve, not just an approximation anymore. So stick around for that.